How can we predict when a redox reaction will occur spontaneously in nature? And by spontaneously, I mean without any external energy. Let's take two examples. We have magnesium solid reacting with copper in solution, copper 2+, to give us magnesium 2+ in solution and copper as a solid. We also have the reaction swapped around. So we have magnesium in solution reacting with copper solid to give us magnesium in solution and copper ions. When we observe these two reactions, we find that the first one occurs quite readily, it occurs spontaneously, but the second one doesn't occur. We don't actually see a reaction without putting energy into the system. So if we look at what's happening in the reaction, the magnesium is going from an oxidation state of 0 to +2, it's being oxidized. In the second reaction, our copper is going from an oxidation state of 0 to +2, so it's being oxidized. If we compare the two, we say that the magnesium is more easily oxidized than the copper is, because we observe a reaction in that first part and we don't in the second one. So we can conclude, because of our oxidation processes, that the magnesium loses electrons more readily than the copper does. In other words, the magnesium is more easily oxidized than the copper is. Now we can compare many different types of metals with each other to see whether we get a spontaneous reaction. We can also do the same thing with non-metals. And we can build up what's called an activity series, where we can compare the activity or the reactivity of different elements with each other. So this table, this activity series table, lists the elements from lithium, which is the one that most easily gives up electrons, right down to our platinum, which is very reluctant to give up electrons. So we have lithium, we have potassium, we have barium, strontium, calcium, all the way through till we get our copper, our silver, mercury, gold and platinum. We can say a few things about this. First of all, as we move down the list, the tendency to lose electrons decreases. Lithium will give up its electron very easily to become lithium plus ion. On the other hand, our gold will be very reluctant to give up its 3 electrons to become gold 3+. We can also say as we move down the list that the tendency to be oxidized also decreases. In other words, we can say that as we move down the list, the elements at the bottom become stronger oxidizing agents. They're more easily reduced into their elemental form. So if we take one example, our gold. We have gold 3+ plus 3 electrons forming our gold solid. A much weaker oxidation process. So we say that it's strongly reduced from 3+ to gold. And this is one of the reasons we see these bottom 5 elements existing in nature in their solid metallic forms rather than their ionic forms, because they're more likely to be reduced rather than oxidized. So our conclusion from this is that a spontaneous reaction will occur where we have any half reaction on the list, so lithium going to lithium plus 1 electron, when paired with the reverse half reaction below it. So let's take an example. If we have iron solid reacting with magnesium in solution, magnesium 2+, to give us iron 2+ plus magnesium solid, we break it down into our 2 half reactions. So we said from our previous slide that if we've got this oxidation process, iron to iron 2+ to give up 2 electrons, we must pair the reverse reaction and it must sit below the iron. So we have iron. For it to occur, the magnesium must sit below the iron. In this case, it doesn't. And that's why, because the magnesium's above, why we don't observe any reaction. On the other hand, if we react iron with lead ions to give us iron ions and lead as a solid precipitate, if we break our two half reactions apart, iron is once again being oxidised, the same as the first reaction, but this time our lead is being reduced. And if we look back at our previous diagram, lead down here sits below the iron, so we would expect when we reverse the lead process, as I've done in the half reaction, that this reaction will be spontaneous. And that's what we observe. When we add iron solid to lead ions, it will definitely give us iron ions in solution and a lead precipitate.